Hello everyone, in this class we will learn a new chapter on sequences. Let's first take a look at a story about a sequence of numbers, where the last digit in the sequence is exactly twice the number before it. German astronomer Titus discovered that adding 0 at the beginning of this column, then adding 4 to each number and dividing by 10, would result in this column of numbers. This column of numbers coincides with the relative distances from Mercury, Venus, Earth, Mars, Jupiter, Saturn to the Sun. If you are an astronomer, do you have any bold guesses based on these numbers? It is not difficult to imagine that at distances of 19.6 astronomical units and 2.8 astronomical units from the Sun, should there also be two celestial bodies separately? Sure enough, astronomers later discovered Uranus and Ceres at these two locations respectively. How about it? This sequence is not simple, is it? In fact, sequences play a very important role in both theoretical research and practical applications. In this lesson, let's first learn the concept of sequence in the first section. How to study the new concept of sequence. A sequence is actually a special function, so let's first review the basic path when studying functions. Let's first present some facts. By using several special examples, common features were summarized and a definition of the function was given. Then we learned 3 ways to represent functions. Then we studied the properties of the function. Finally, we studied several special functions. We learned sequences by analogy with the basic path when studying functions. Since that's the case, how can we define a sequence? Starting from facts, from special to general. Okay, next we will abstract the definition of a sequence through a few special examples. The first example is a real-life problem. Wang Fang's height is arranged in this column from the age of 1 to 17 each year. May I ask if they can exchange positions? Is there a definite order? Let's analyze this issue. Wang Fang's height at the age of I is denoted as hi. Please pay attention to this notation. I is the subscript written in the lower right corner of h, and I can take a positive integer. When I equals 1, it is Wang Fang's height h1 at the age of 1, which is 75. Similarly, h2 equals 87, h3 equals 96, until h17 equals 168. The I in hi reflects the determined position, that is to say, h1 is equal to 75, which is the number ranked first. h2 equals 87, which is the second digit. h3 equals 96, which is the third ranked number. Until h17 equals 168, it ranks 17th. Of course, they cannot exchange positions between them, because once the position is exchanged, the meaning it represents is completely different. So these numbers have a definite order. Let's take a look at the second example again. This is an example from the history of mathematics. It's a clay tablet from the 7th century BC. If we divide the full moon into 240 parts, then the visible part of the moon from the first day to the 15th day can be represented by a number representing the score. On a clay tablet excavated in the Two Rivers Basin, there is a column representing the number of visible parts of the moon from the first day to the 15th day of the month. Can they exchange positions between each other? Is there a definite order? Let's compare the expression method of the previous example to analyze this column of numbers. If the number of visible parts of the moon on the first day is I, then the number of visible parts of the moon on the first day is S1, which is 5, and this is the number ranked first. Similarly, S2 equal to 10 is the second digit. S3 equals 20, which is the third digit. Until S15 equals 240, it ranks 15th. They cannot exchange positions between each other, so this column of numbers also has a definite order. Let's take a look at the third example, the negative 1/2 power of n. We arrange the negative 1/2 powers of first, second, third, and fourth idempotent in sequence. Okay, the next task is up to you. Can you follow our description of the previous two examples and demonstrate that this is also a column of numbers with a definite order? This shouldn't be difficult. In fact, the 3 specific examples we just presented are all sequences of numbers. Let's summarize the common features of these 3 examples from a compositional perspective. They are all a column of numbers, and the positions between the numbers cannot be interchanged. So we just said that this column of data has a definite order. Generally, we refer to a column of numbers arranged in a determined order as a sequence, and each number in the sequence is called an item of the sequence. Regarding the definition of a sequence, it must be noted that it is a column of numbers arranged in a determined order. For example, are these two sequences the same sequence? According to the definition of a sequence, the numbers in a sequence have a sequential order, so even if two sequences contain exactly the same number, as long as the order of arrangement is different, they are definitely not the same sequence. Okay, let's take another look at this question. Is this a sequence? Is that so? We only require the numbers in the sequence to be arranged in a certain order, without specifying that the numbers in the sequence must be different so the same number can appear repeatedly in a sequence. Okay, earlier we studied several specific sequences that are different from each other. Can you use general symbols to represent them? We know that a sequence is a set of numbers arranged in a predetermined order. We can use positive integers to represent the determined order. We use a1, a2 up to an to represent the first term of a sequence, also known as the first term. The second item continues until the nth item. The general form of a sequence can be written as follows. Simply put, an should be enclosed in a curly bracket. Are the meanings represented by these two symbols in the sequence the same? It's different. N only represents the nth value in the sequence, and adding a curly bracket outside n represents a sequence, and we usually add the word sequence in front of it, which is the sequence n. What are the characteristics of the number of terms for different sequences? Let's still look at these three sequences. Firstly, the first sequence has a total of 17 items, and its number of items is 17. The second sequence has a total of 15 items, and the number of items in both sequences is finite. But the third sequence is different. Its number of items is infinite. In this way, we can divide a sequence into the following two categories based on whether the number of items is finite or infinite. We call a sequence with a finite number of items a finite sequence, while a sequence with an infinite number of items is an infinite sequence. Previously, we learned about the concept of sequences. Based on the concept of sequences, we know that there exists a corresponding relationship between each item in a sequence and its sequence number. What is this correspondence relationship that we have learned before? Do you have a feeling of familiarity? For any positive integer n, there is a unique and definite number n corresponding to it. So in fact, a sequence is a function composed of ordinal and polynomial terms. We mentioned in class that a sequence is actually a special function. Next, please observe these two sequences. Are they the same sequence? Perhaps when you see that the number of items is different, it is not the same sequence anymore. Now is the time to test you. Since the sequence is a special function, can you explain from the perspective of a function why these two sequences are not the same sequence? Is the domain different? The domain is the range of values of the independent variable. For a sequence, the independent variable is the number n. For the first sequence, n can take any positive integer, so its domain is the set of positive integers. It is an infinite sequence. And the second sequence is a finite sequence, whose domain is actually a finite subset of the set of positive integers. Because the domains are different, they are certainly not the same sequence. The key to solving the problem we just encountered is to treat the sequence as a function and conduct research. So it is necessary for us to further study the functional characteristics of sequences in order to have a deeper understanding of sequences. Let's first take a look at the domain of a sequence. Through our analysis of the problem just now, it is not difficult to conclude that the domain of a sequence is the set of positive integers or its finite subset. What is the range of values for the sequence? That is, the range of values for a n. Anyway, we can see that a n must be a real number. So the range of values for a sequence must be a subset of the real number set. In this way, we can say that the sequence a n is a function from the set of positive integers or its finite subset to the set of real numbers. We denote a n is equal to fn. When we study functions, after learning the concept of functions, we also learn the representation methods of functions, including list method, graph method, and parsing method. As a special function, the sequence should also have these three methods. For example, this sequence. We can use such a table to represent it. We can also draw its image. When we look at this image, it seems to be different from most of the function images we have seen before. It is broken by a point instead of continuous. What is the root cause of this phenomenon? Is it a domain definition? Most of the independent variables in the functions we learned before are continuously changing, and the independent variables of a sequence can only take one positive integer after another, so its image is naturally composed of isolated points. In addition to the list method and graph method, the representation of functions also includes the analytic expression method, and the sequence should also have an analytic expression. If the correspondence between the nth term n of a sequence and its index n can be represented by an equation, then this equation is the functional analytical formula of the sequence, called the general term formula of the sequence. For example, the sequence we mentioned earlier is composed of -1/2 powers of 1, 2, 3, 4 idempotent, etc. So a common formula for this sequence is naturally that n is equal to -1/2 to the power of n. So what is the function of the formula for the general term of a sequence? If we know the general term formula of a sequence, we use n equal to 1 to obtain the first term, a 1 equal to a power of -1/2, which is -1/2. If n is equal to 2, then the second term, a 2, is equal to the second power of -1/2, which is 1/4. Is that just a general term formula for a given sequence? So we can write out each term of the sequence, which is the function of the general term formula for sequences. According to our research path, the next step is to study the properties of sequences. For functions, we first study their monotonicity, and for sequences, we also take a look at their monotonicity. Let's take a look at this column of numbers. Can you find the pattern of the items in this sequence changing with the sequence number from its table and image? We can see that starting from the second item, each item is greater than its previous item, and the image also reflects this characteristic. So, in this way, we call the sequence from the second term onwards, where each term is greater than its predecessor, an increasing sequence. Allied. Starting from the second term, a sequence in which each term is less than its preceding term is called a decreasing sequence. If all terms of a sequence are equal, we call it a constant sequence. For example, the sequence we mentioned earlier is 1. Next, we will consolidate the knowledge we have learned in this lesson through 2 example questions. Firstly, the first question asks you to write down the first 5 terms of a sequence based on the general formula and draw an image. Let's take a look at the first one first given the general formula. So we can use n equal to 1, 2, 3, 4, and 5 respectively to write out the first 5 terms of this sequence, which are 1, 3, 6, 10, and 15. Then we will trace the points according to the table. Please note that no more lines can be drawn here, as the image of the sequence is composed of isolated points. For the second one, we can use the same method to write out its first 5 items and draw its image. Okay, now let me add another question. Can you determine the monotonicity of this sequence? Starting from the second term, each term is greater than its previous term, so it is not difficult to determine that this is an increasing sequence. Let's take another look at example 2. Write a general formula for a sequence based on the first 4 terms of the following sequence. Firstly, let's take a look at its patterns. In terms of absolute value, the absolute value of the first term is 1, the absolute value of the second term is 1/2, the absolute value of the third term is 1/3, the absolute value of the fourth term is 1/4, and the absolute value of the nth term is naturally 1/nth. From the perspective of positive and negative signs, its characteristic is that it has both positive and negative signs, and the positive and negative signs are alternating. So how should this characteristic be represented? We often use the nth power of -1 or the sum of the powers of -1 and n to represent the variation pattern between positive and negative phases. For example, when n is odd, it is -1, and when n is even, it is +1. So when we multiply by -1 to the power of n, we have alternating positive and negative values. Of course, the odd terms here are positive, while the even terms are negative, so we should multiply by -1 to the power of n. In this way, we have written a general formula for a sequence, where en is equal to n divided by -1 plus a power. Let's take a look at the second one. In this sequence, the odd terms are 2 and the even terms are 0. We can write the odd terms as 1 plus 1 and the even terms as 1 plus -1. How can we make the odd terms be 1 and the even terms be -1? We just talked about it. Is it enough to add n to the power of -1? In this way, we have written a general formula for a sequence, where a equals n of -1 plus 1 power and then 1. The above is the knowledge we have learned in this lesson. In this class, we studied the research path of analogical functions and learned about sequences. We first presented some facts and then defined sequences through mathematical abstraction. We call a column of numbers arranged in a determined order a sequence. Then we analyzed the concept of this sequence and found that it is essentially a special function. Then, by analogy with functions, we learned 3 ways to represent sequences. Finally, regarding the properties of a sequence, we have defined its monotonicity. That's all for this class. Goodbye, everyone.